what goes wrong if I want to use some state operator map in a QFT that is not conformal? Like, for example, if I'm in a free theory or in something similar to a free theory and I have some annihilation creation operators, like, cannot I make similar statements even if it is not a conformal?
So if it's a free theory, it's conformal, pretty much. Well, not quite. 3D free gauge fields are not conformal. So what do you mean creation and annihilation operators?
I expand my fields in Fourier modes.
Where?
I mean, I'm thinking
on a sphere? Or
just at time slice of the space-time.
Okay.
And there, cannot I think that an operator acting, like, cannot I make something similar? I have an operator, I act it on the vacuum, and that gives me a state? Or is it about radial quantization?
Okay, so it's definitely true that an operator acting on the vacuum gives you a state. Probably now we could discuss normalizability of that state, or how to now even in the case of SFT and where I'm on a sphere, these are not the states that we associate to operators in the state operator map. Let me elaborate. So if I act with dx of S, say, on the vacuum, this gives me a sum of e to the ns, maybe minus ns, I forget, a minus n acting on the vacuum. On the other hand, our objective was, when the state operator map, I would associate dx to a minus 1 acting on the vacuum. So I really need to take the limit as this goes to minus infinity to produce a state. Okay. So essentially, it's like I'm picking the lowest energy state, the lowest energy eigenvector I can find in the state created by my operator. So I create something, but I put the operator very, very far in the past. This is typically not a great limit, right? Most operators acting on the vacuum give me a sum of things which include the vacuum. And so when looking if I evolve for a whole time, I just get back the vacuum. Now, if I can perhaps make sure that my operator doesn't have an exploitation value, so that it doesn't happen. But then, if I'm in flat space, there is a continuum, right? What's the next thing I can create? I can create a particle, perhaps. But many operators will end up creating that particle. So now, if it's not a conformal field theory, as I was mentioning last time, the space of operators has, not that much structure. So, yeah, you can probably start building up, the operator that creates this particle, and then perhaps an operator that creates two particles, it's still a bit sketchy to try to sort of take this limit to the past, because if an operator creates two particles, well, they go in different directions, and what I get still depends on how much time has passed. And there's also the issue that it becomes, it's a related issue, but it becomes a bit tricky to figure out which states were created by a local operator. Right here, we are trying to talk about local operators, not just observables placed in some arbitrary large region in space-time. So, right, I don't know of a natural way to really attach states to operators. Although, conversely, if you think about observables instead of local operators, the way you build the Hilbert space of a quantum field theory is precisely to take a vacuum, act on it with observables, and then sort of take the normalizable completion of that. So you can definitely build your Hilbert space out of observables. It's the part about local operators which is really specific to conformal field theories. And intuitively, this is because conformal field theories have a scaling symmetry that allows you to take an observable and make it very small. So conformal field theory sort of comes with a canonical way to build local operators out of observables, which is to shrink the observables. In a quantum field theory which is not conformal, if you try to define a local operator, you had to sort of give me a sequence of observables which are supported on a smaller and smaller region. So it is much less canonical. You need to give me a new definition for every region. And yes, local operator, I mean, I have to say, the more I work with, the more I feel that local operators for non-conformal field theories that are not conformal, are really messy to talk about in a sharp way. But it's hard to do without them, because observables are just, I have no idea how to even talk about which are the observables of a general quantum field theory. While in an asymptotically free quantum field theory, I can imagine the local operators kind of resemble whatever free theory I have, description I have at short distances. Even the statement, I don't know how sharp it is. But intuitively, if I study Emil's theory, I expect to have an operator that kind of looks like trace of f squared. Okay, there will be a normalization, there will be complicated things happening, but I really hope that there is something that looks like that. And which I can define by saying, okay, maybe I vary my gauge coupling a little bit in a region, in a tiny region, infinitesimally. And that's the same as inserting the operator trace of f squared in there. Something like that. Right. But yeah, I don't know. There are many axiomatizations of quantum field theory, and to be frank, I'm not terribly familiar with many of them, because many formalizations had the terrible tendency to be a bit too strict and to they always seem to me that, a lot of them seem to have built in too much of free field theory. But I think, people are, I think there are some reasonable axiomatizations. It's just very hard to connect them to concrete things. Algebraic quantum field theory is a very tough subject. Although progress is happening. Progress is happening. Steady, slow perhaps, but steady. For example, I don't know, if a few years ago, mathematicians managed to prove that something called Liouville theory exists in 2 dimensions, which is a 2-dimensional quantum field theory, so it's nice. And recently, people have been using ideas from algebraic quantum field theory to discuss things like the information paradox and black hole physics or cosmology. But again, I'm not an expert in the subject. I'm trying to learn a bit more. So yes, it's the basics of quantum field theory are still a little bit open as a subject. And some of these basics, can become very concrete in the sense that, I don't know, another thing that is progressing is our ability to simulate or compute in quantum field theories, like new ways to think about lattice systems or not lattice systems, like in-chain sphere, fuzzy sphere regularization, and the conformal bootstrap. All of these new computational tools really give us a way to work with quantum field theories at strong coupling. And so I expect our understanding of how quantum field theories look like will accordingly improve. Any other questions? Okay, so where are we? Last time we looked at the scattering of 3 tachyons, and we found that it was 1. I was thinking perhaps to give an example of a slightly more complicated scattering amplitude of 3 things, like a graviton scattering of a tachyon. Something in the quantum field theory I would describe like that. I have a scalar which emits a graviton. So we wrote at some point the states which corresponds to tachyons. I still don't know why the chalk does this. This is not legible, right? This was a state for the tachyon. Then we put the Gauss there too. And then for the graviton, we had something like A minus 1 mu, A minus 1 nu, B, so G. Okay, I call it graviton. Really, in here, if I don't do anything to these indices, I might have inside the graviton the B field, which was this 2-form field coupled to strings, and the dilaton, which was this scalar field. So all of the massless fields are here. Let me just put them all here for now. We can worry later about splitting out some part of it by playing around with the polarization. So let's apply state operator map. We know this goes to e to the I p x c, c bar. Where does this go?
Del x mu, epsilon.
Right, so on the state operator map, every a minus 1 comes from a dx. And so I can write something like that, dx nu, e to the I px c bar. Now, what does it mean when I multiply this by these sort of things? So in the plane, what this means is that I'm just not doing with contractions between things I'm multiplying. So as long as I work on the plane, I can just use normal ordering, which is very, very safe and easy. And we learn how to map all calculations to the sphere, which is the same as the plane, with a little bit of care if I put an operator at infinity. Okay. Remember that this is BRST closed, only if it's killed by Q, which concretely means that epsilon mu nu p mu has to be 0, and epsilon mu nu p nu has to be 0. And then the answer should not change if I shift epsilon by something proportional to p. And also p squared is equal to 0 here. Well, p squared was equal to 0 to 2 here. OK. So we already know what the ghosts do, right? The C, 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 C. Just gives us the product of Zi minus Zj squared. So what I need is the correlation function of things like e to the I p1 x of Z1, e to the I p2. At some point, I could put the points at 0, 1, and infinity, but I think it's still instructive to see BRST invariance doing its magic. OK. So how do I compute something like that? I mean, if you forget about indices, OK, let me just do it in one for one single scalar, and then we'll put it together.
Because I have to contract the del x into exponentials.
Actually, this, yes. Yeah, you're right. In principle, we could just be very patient and do with contractions. So we're going to have to do the contraction between these. I have to contract this sometimes with exponentials, sometimes with other things. It's absolutely doable. There is a trick which might be helpful, which is the following. So suppose that I have a bunch of normal order exponentials. OK, sorry, I don't want to say this wrong. Sorry. What's the simplest way to do this? So sorry. So I have the answer, but I just wanted to see. So I wanted to correct this mistake that was going to kill me. So, yes. So one way is to use, if you want, conformal field theory techniques too, and think about what's the OPE of del x with an exponential. So del x is a current, and these exponentials are what are called primaries for the current, meaning that they are very simple, just have a simple pole when the current goes close to the exponentials. So one way to do this is to say, OK, let me put this at z instead of z1, z2, z3, and then find the answer and throw away the part that comes from the normal ordering. And when I look at this as a function of z, well, it has a simple pole at a bunch of points. Does not grow. It goes to 0, and I send z to infinity, and I can find an answer. That's how you would probably see in calculations like that done in conformal field theory. Then doing reconstructions is also an option. It's a bit tedious, but it's an option. There are a variety of manipulations one can do. And the final answer, you can really see these simple poles I'm talking about. Like the final answer is of this form. So actually, I think the most natural way to think about this calculation is the following. You can think about these exponentials as things you just put in the action. So you can pretend that the action is the integral of del x del bar x plus just sum of PA x evaluated as ZA. It's like an extra linear term in the action. And so you're doing a Gaussian path integral with a quadratic and a linear term. So you're doing a two-point function, because now you've moved this to the action. You're just doing a two-point function with this in this Gaussian integral. And pretty much you get the classical solution for x, for del x and del bar x with this action. This action gives an equation like Laplacian of x is equal to sum of p a delta of z minus ZA. So the classical solution is just a sum of Green's functions. And so this is literally the expectation value of this in this classical solution. And this is the expectation value of that. So just wanted to remind you, all different strategies you can use to get to an answer like that. In any case, we can now combine it with the polarizations. We can throw in the ghosts. And we need to plug in the on-shell condition. So I plug in these conditions, which allow you with a bit of work to rewrite this as minus 2, 2, 2. And okay, this still looks like it depends on the z's. So you might find it bothersome, but we still haven't used the fact that P3 is orthogonal to epsilon. And you can use that and momentum conservation to manipulate these expressions a little bit farther. Essentially, the point is that you can use epsilon mu nu P3 mu equal to 0 to learn that epsilon mu nu P1 mu is equal to minus epsilon mu nu P2 mu, which allows you to sort of combine these terms and combine these terms in a nice way. Look at the difference of these fractions. The difference of these fractions is something very nice. It's something like Z1 minus Z2 over these two denominators. Same here. So the whole thing gets reabsorbed into here, and it cancels these factors. So you get to something that doesn't depend on the 3 points, as it should. And this is a pretty reasonable interaction vertex for a spin through, in a quantum field theory. If you think about the graviton, for example, which is the part where this is symmetric, but first of all, notice only the part that is symmetric survives. The B field, the antisymmetric part, does not couple to the tachyon directly. And the graviton, well, if I had a scalar field, this tachyon, the graviton would couple to the tachyon to some to something like that, right? If I change the metric a little bit, if I start from something like roughly, right? Okay, there is going to be some other term which has to do with the trace of H, but I'm not going to try to get into detail. But if you just write down how a scalar field couples to a metric in space-time, don't confuse this with the HAB that we're using on the worksheet. Then you get an interaction vertex which has 2 momenta. Maybe I should put it like that, sorry. Like a change in the metric of space-time. Would give you an interaction vertex like that. So it's pretty reasonable. Now, I will ultimately get to sort of, I will show you how to really see that the graviton you find here will always couple like a graviton and so on. But for now, you just see that the interaction is reasonable. One thing I could say is that if you just work in an effective field theory and you try to write down the couplings of a spin-2 massless particle with stuff, you'll find that there are all sorts of interesting constraints. So pretty much from the requirement that nothing blows up when the momenta of the graviton go to 0. This goes a bit outside our discussion, so I'm not going to show details, but you can find some reviews on this. So both for massless gauge fields and massless gravitons, gauge invariance is quite restrictive on the sort of couplings that you can find in an effective Lagrangian. So when you have a gauge invariance, a spin-2 massless particle with gauge invariance, pretty much has to couple to a conserved stress tensor. So and its effective action pretty much has to be the one of Einstein gravity plus higher derivative corrections. So here we have the correct gauge symmetries and the correct on-shell conditions. So as long as you can convince yourself that string theory kind of looks like a quantum field theory at low energy, then the interaction kind of had to have the correct form. So I would like to discuss perhaps a little bit why do I expect a string theory amplitude to look like a quantum field theory amplitude. I mean, the physical intuition is that, as we've seen, there are a string as an extended object has infinitely many states, internal excitations, but they have increasing energy, increasing mass. So if I go at low energy, I only see the low energy states, which, as you see, are the tachyon and the graviton and dilaton and B field. But I think we can do a little bit better than that. I mean, ultimately, we're going to compute a 4-point scattering amplitudes, 2 tachyons coming in, 2 tachyons coming out. But before I get into the sort of nitty-gritty of the calculation, I would like to illustrate why that calculation will give us something with certain properties. So before I move on, any questions about this calculation?
So it kind of looks like coupling this H mu to the T mu, right? But isn't there like this Weinberg-Witten theorem which says that there is no T mu or something like that?
I didn't say that T mu is an operator. I'm saying that it couples. I'm just saying that the graviton couples to some interaction terms which look like a conserved stress tensor when I turn off the metric. When I include when I include all the couplings, I'll have covariant derivatives and things like that. So the coupling in the Lagrangian is gauge invariant. What's not gauge invariant is placing a stress tensor at some point in space-time. Pretty much no local operator is gauge invariant in gravity, not just the stress tensor. Because if I add to the diffeomorphism, it moves. And diffeomorphisms are gauge symmetries. On the other hand, right, the Van Bergen theorem is the observation that a quantum field theory has a stress tensor, which is gauge invariant. At least in a quantum field theory defined by standard. At some point, you could say this. Of course, what do the words quantum field theory mean? I think in that theorem they meant it as, okay, something I make out of a bunch of fields, of standard fields of spin 0 and spin 1. Then you say, okay, that one has a stress tensor. The stress tensor cannot just disappear at low energy. What disappearing means becoming inconsistent. If I had a question that was reasonable to ask at short distances, it will still be reasonable to ask if I look from far away. And then you can sort of extend the theorem to sort of include CFT in the UV. And at some point, the stress tensor might become just, the existence of the stress tensor at some point becomes sort of a part of the axiomatics of a quantum field theory. But once you get there, then clearly you'll never get gravity in the infrared. Then, of course, the whole discussion becomes, okay, so which UV things are not quantum field theory and could get around this no-go theorem. At the end, the theorem is just a formalization of the idea that kind of, I don't know, in gravity you should not be able to ask questions about individual points of space-time. The quantum field theory is essentially defined as a theory where you can ask questions about individual points of space-time. And if you're able to ask those questions in the definition of the theory, you will not lose suddenly this ability when you're at low energy. Okay. Now, I would like to sort of just think together about what does it mean to speak about the complex structure or the shape of a surface like this. So if I were to ask, suppose that, so we did a 3-point function, we got something nice. So let's assume that we have some canonical, and we said there is just no moduli in the case of the 3-point function. So I can always map something like that to a sphere with 3 punctures. And I put the 3 punctures at 0, 1, at infinity. Now let me pick some canonical shape I like. You know, they're all going to be equivalent to this. But suppose I give you this gadget. Can you use this gadget to make something that looks like that? So I'm giving you this, like a piece of plastic. I pass it to you. What can you do with that to make a piece of plastic that looks like this? Mm-hmm.
I can put 2 of them together, like join.
Yep, absolutely. You could say, okay, I take this piece of plastic, I take another piece of plastic that looks the same, and I join them. I was drawing these asymptotic tubes in such a way that they were actually semi-infinite cylinders, so I can cut them and glue them together to get a finite piece of cylinder in between. And that is perfectly fine to do so. Now, how much freedom do you have in doing this gluing procedure?
Freedom in what sense?
If I glue it and you glue it, we'll always get the same thing.
Because the cylinder can have different lengths, right?
Right, we made some choices when we cut and glued. There are two choices. How far do we go with the cut? How long is this cylindrical region? And how much did we twist them with respect to each other? So here there was sort of a marking here. And maybe this marking here is misaligned with the marking there. There's some angle. There's an angle and a length. Okay. Now, nothing prevents me from now. Suppose I want to compute a CFT worksheet correlation function on this geometry. Nothing prevents me from using this complete set of states here. This cutting and this gluing can be done by summing over a complete set of intermediate states. So I have something like a state, sum over states. I have my I insert pairs of states in the two surfaces. And then what controls the twist and the length? Well, pretty much the momentum and energy of the states on the cylinder. So something like e to the I theta p of we call it A, P of A, and e to the minus L E of A. Right. The more we evolve, the more we suppress states which have energy. And rotations are done with translations along the circle. So this is the direction we were calling sigma. This direction we were calling tau when we're talking about the cylinder. So, I mean, in terms of the Virasoro mode, this P of a state was like the L0 minus L0 bar acting on a state. And the energy of a state was something like L0 plus L0 bar minus the Casimir energy. Right, something like -1 if I include everything, matter and ghosts. So now I'll tell you that the moduli space of complex structure for this surface is one complex dimensional, so it's two real directions. And here we describe a patch in this moduli space, which is parameterized by this L and this theta. You're not going to be able to get all of these surfaces like that, but you can get some. And what happens if I integrate over these surfaces? I have something like a dl and the theta. I also need to put some big ghosts. Let's not worry too much about that. It's something like a B0, B0 bar. Pretty much because I'm integrating over variables which are dual to L0 and L0 bar. All right, the details don't matter very much. All I want to say is that the integral over theta, so theta varies on a circle from 0 to 2 pi. So the effect of the integral over theta is just to force L0 to be equal to L0 bar. So instead of summing over all the states, we'll sum over all the states such that L0 is equal to L0 bar. And that will deal with the integral over theta. And what you're left with is an integral over L from some minimum value to infinity. And what's in front of L? There is L0 plus L0 bar minus 1, which, if you remember, if I'm acting on any state that is built from the integral space of the scalar field, will have some contribution from the momentum and then something that comes from the modes that I had added on top of that. So now, did you ever find yourself in a situation where you're computing something in quantum field theory and you have an integral so here we're summing over all states, right? Summing over all states includes both an integral over momenta and a sum over whatever oscillators we're adding on top. So there is a sum over oscillators that I'm just going to put a question mark on. There's an integral over momenta. Then we have e to the minus p squared plus some integer. Times this length. And then some stuff. Now, have you seen something like that? Perhaps in our second lecture? Or do you see something like this?
Is it like Schwinger parameterization or something?
Yeah, absolutely. This looks like a situation where I have some Feynman diagram and then a line with some momentum propagating. And I'm trying to write the propagator, 1 over p squared plus m squared, as an integral of e to the minus L p squared plus m squared from 0 to infinity. Here, there was some minimum L, I go all the way to infinity again. And this L is really sort of a Euclidean proper time for this particle. How far is this particle going in the interaction? So you see that the string theory integral is kind of giving us the tail of this integral where the particle has propagated for a while. So I'm kind of finding an S-channel diagram in there. But of course, I could have glued my surface in other ways, right? I could have perhaps glued it like that. Or perhaps, and now I'm so bad at drawing T-channels, but U-channels, sorry. Arg. I don't know if I can draw this properly. I apologize. Anyway. So, and it just so happens that surfaces you get like these for sufficiently long L never have the same complex structure or surfaces you get like these or like this. So the space of complex structures, we call it M 0,4, and I want to use a different color because I really don't want to confuse it with this worksheet itself. The space of complex structure sort of has corners. One corner is parameterized by theta in the S channel and L in the S channel. Then there is another corner which is parameterized by theta in the T channel and L in the T channel. Another corner which is parameterized by theta in the U channel and L in the U channel. And then they meet in between in some way. Okay, I know this looks like a worksheet, but this is not the worksheet. This is a space of complex structures for that worksheet. Apologize for the resemblance. So this part of the integral will reproduce pretty much field theory amplitudes that look like that. This part of the integral will reproduce quantum field theory amplitudes that look like that. Or Feynman diagrams will look like that. And this part will reproduce things that look like that. And then depending on your conventions, there might still be a blob in between which is not covered by any of these parameterizations. It's just something which is, fat in all directions. It's not easily cut in any nice way. And this will give us sort of an extra term. If it looks like that. So inside the string theory amplitudes, we can find pieces which reproduce some field theory amplitudes. And these pieces will look like they have some tower of intermediate particles with the correct masses. Now, to make this precise, you might use something called string field theory, which is about really trying to cut this into pieces that look like quantum field theory. But even without going that far, you can sort of still recognize some aspects. For example, quantum field theory amplitudes have poles and singularities when the momenta of the intermediate particles go on shell. These poles come from a long propagation in time. And so they come from a part of the integration region, which is definitely still there. So all of the interesting poles and features that come from particles propagating for a while are there in the string theory amplitudes. What you don't get are singularities that come from short propagation, UV singularities. UV singularities in quantum field theory come from the helical, from the short distance part of the Schrödinger integral, and those are just not there. They are replaced by this smooth joining. So, right. So in general, all subtleties you find when you look at string theory amplitudes are infrared subtleties, and you treat them in the same ways you would treat them in any quantum field theory. And you don't get UV divergence subtleties. Whenever you think there is something which looks like a UV divergence, was actually an infrared divergence in a different channel. So that's nice. Okay. So I'll set up the calculation and we'll do it next time. Actually, instead of setting up the calculation, let me do a few more observations. So there's sort of two ways to write the Schrödinger time integrals. In this way of writing the propagator using Euclidean time on the particle word line. This is great if p squared is large and positive, not so great if it's negative. And sometimes it's perfectly possible to have a situation where the outside particles are on shell, but the intermediate momentum is not on shell at all, and it might well be negative. So this doesn't work very well for that. What you can do in quantum field theory is instead using something like this. This is brutally oscillatory, but it's not bothered at all by p squared being positive or negative. And then if you have an I epsilon prescription, you're fine. I don't remember if those plus or minus here, forgive me. I need to double check. It depends on if I put a plus or a minus here. So if you have an epsilon prescription on the momenta, you can use Lorentzian time, Lorentzian proper time for the particle. And It's nice. Now, meaning it's well defined and you don't have this apparent divergence. So in quantum field theory, there are sort of two ways to go. You can do the calculation like this, or you can do the calculation like this while keeping the external momenta in regions where this converges, and then analytically continue back to the region you were interested in. So this is something that happens in quantum field theory if you use the Zwinger time formalism. And the same thing will happen in string theory for the same reason. So if you do calculations with a sort of Euclidean worksheet, your length, your gluing length behaves like an Euclidean time, and you get something like this, and you deal with it. And the same way as you would do here. Or you can try to sort of push things into the Lorentzian worksheet direction. Notice that in practice, you don't need to change the whole integral. You're only bothered by the part where L is very large. So you can sort of go, this is the L plane. You can go for a while along the real axis and then take a walk in the imaginary direction. So same here. Once we write our final expression, where there are going to be some variables which are analogous to L and theta, we could do like Polchinski and do calculations on the naive integration contour, but keeping the outside momenta in a convenient region. Or we could do an analytic continuation of the integral, which is completely analogous to sending the Zwinger times to be Lorentzian in the region of integration where I have a particle that is propagating for a long time. Mm-hmm.
Is this equivalent to just dividing by 1 over p squared?
What do you mean divided by 1?
Because there are going to be some problematic states. I don't know, maybe if I have like propagating tachyon or something,
mm-hmm.
but I could just do finger parametrization and I could just like divide.
This is not about tachyons, it's about all particles.
Yeah, so anything which has negative p squared, I could just use the 1 over p squared plus m squared on it, and I wouldn't have to, and then I wouldn't get a divergence.
Well, the problem is that the integral I'll have very complicated functions of L, which have this exponential behavior as L goes to infinity. So the string theory amplitude is not going to have just an e to the minus L. Okay, if you decompose it like that, sure. If you say, okay, if I do string field theory, I just put the propagators by hand, and that's perfectly fine. But if you don't want to know string field theory, you don't want to do this sum of a very complicated collection of states. You want just to use your CFT abilities to compute stuff here and integrate. Well, then you'll have some complicated function of your complex structural moduli. It's a function which in some corner of moduli space looks like it has an exponential decay. You would like it to have an exponential decay, but in the intermediate momenta. Anyway, we'll see what happens, okay? But just to say that there are these two ways of dealing with it. This is the Polchinski one. And here you can find in some recent papers by Witten. But again, I want to stress, this is not string theory subtleties. All of this affects the region of integration where you're really talking about quantum field theory. So you never need to do more or less than you would do to define a quantum field theory amplitude. In the right. Okay. So the CFT part of the calculation, once you mapped it on a 4-particle sphere, is very straightforward. I need to do something like, C bar e to the I px of z1, C bar e to the I px of z2, C bar e to the I px of z3. And as we discussed last time, I only need to do e to the I px of z4 for the fourth leg. So pretty straightforward calculation. At some point, of course, I can do the calculation keeping along z1, z2, z3, z4, and see that at the end, 3 of them drop out. But, or I can put z1, z2, z3 to some convenient values. It's like 0, 1, and infinity. But be as you want, what we need to do is the integral of this over the square z4. So this is the definition that we need. So, and can you guess which regions of the integral correspond to those regions? That's not obvious at all at first sight. So what could I possibly be doing to these 4 points? Really to one of the 4 points, because the other 3 I can keep fixed. What can I do to this to get to a sphere which would come from this?
Maybe a collision or something?
You set it to, set it to infinity?
Infinity where? Sorry. So here I've
Oh, you already said, okay.
So there is a point on the sphere which is infinity, but it's not different from any other point. Perhaps you meant if one of these points is the infinity. But let's try to derive it instead of guessing. Of course, having a point going close to another point is the simplest way to treat one point different from the others. And here, definitely, if I call this z4, z4 is treating z3 in a different way than it's treating z1 and z2. But let's collapse the legs. Right? If I collapse the legs, I'll have 2 points here. Then I had this long tube and 2 points here. Okay, so which kind of wild factor can I put on this to make it look like a sphere? I need to either collapse this thing in or collapse this thing in. If I collapse this thing in, this whole thing will be squeezed down a lot, right? So that this region gets mapped to this region. And the longer is L, the more these 2 points will end up close to each other. Just a radial quantization sort of thing, right? If this distance is L, it means that I'm squeezing here by a factor of e to the minus L. So yes, I get this region where 2 points are colliding here. And more precisely, I want the distance between the 2 points to go like e to the minus L. So I mean, it's reasonable that the dangerous situation when you have a correlation function is when operators collide. So here I'll encounter some danger when z4 hits z1, z2, or z3. And this danger will correspond very literally to these parts of the integral. So we expect to see something like, you know, n e to the minus L times some momentum, right? Something like that. And in here we find something like Z4 minus Zi to some intermediate momentum squared. So here I said I was integrating over momentum, but sorry, I don't know why I wrote that. I meant this. My bad. The momentum is determined by that. It's just the sum of the momenta coming in. Okay, so next time we're going to write the integrand, and then we're going to integrate it.
Sorry, can you explain again why those 2 points collapse into one?
Yes. So
why can't I just like? Why am I not allowed to just shrink the 2?
So let's see, how do we change this distance? That's the easiest way to see it. We change this distance by e to the minus L times L0 plus L0 bar. Where L0 refers to sort of the zero mode of the stress tensor along this circle. Now, if I draw my sphere a bit bigger, that dotted line becomes this dotted line. So I'm acting with L0 on the pair of points. L0 implements the dilatation. So changing L0 literally means taking this picture, shrinking it, and gluing it back. So adding a little time evolution here is like shrinking this and putting it inside. So as that's one possible way to see it. The other way is to just write down a Wald factor here, and see that it makes this distance very short. Now, you might find confusing that I'm saying, oh, I make these 2 points very close, and I don't touch these 2. Now, there is indeed a conformal transformation, which is just the dilatation, which gives you an alternative picture where these 2 points are at finite distance, and these ones have been made very close. So this is sort of part of a more general pattern. These sort of corners of moduli space always look like I have some surface with some points, some holes and stuff, and then I have a tiny long tube, and then another surface. Or perhaps the tube is between the surface in itself. That was a situation where I've sort of added a handle that joins 2 things. And these are sort of all the possible things that can go wrong as you study the space of compact structures. Space of compact structures has a boundary. Okay, it's an open thing, and you can close it to get a boundary, and the boundary consists of sort of all pictures that you can draw like this, where the surface sort of breaks into 2 pieces. And the corresponding potential problems correspond to situations where you have a particle propagating between two blobs.
So somehow all the stringiness comes from the interior of the moduli space.
All the what, sorry?
Also stringiness.
Yes, yes, I think that's fair. I think that's fair. So the moduli space has these boundary regions, these non-compact regions, where you compute things that have to do with quantum field theory. And then inside there is the stringy stuff that cures UV divergences.
This is independent of where the strings are propagating?
Yes, yes, these are pretty universal statements.
Can you explain the U channel case? Like, because I would have to put together Z4 and Z2, I think.
Yeah, that's right. I mean, I can bring Z4 close to any of these other points. I mean, I'm calling the ST and U, but it's purely conventional. And you know, if you have more legs, you can get sort of hierarchical things. You can say, okay, I'm sending this 2 point close to the third point, while they're also getting close to together in some way. You can get sort of pictures like this. If you try to write it as a sphere, here would have, okay, I have these 2 points are going together, but also these 2 points. Or perhaps these are fixed, these 3 points are coming together, but in a hierarchical way. Yes?
So somehow open strings are less stringy than closed strings because I can sort of fill the whole moduli space with cubic vertices. Is that true? Or?
I think that's fair. So this is they're not discussing instead about string field theory. This attempt to break down the whole integral into convenient regions. We haven't discussed open strings yet, but it is true that open strings are easier to cut for reasons I'm not completely clear why is that the case. So you can make open string field theory look like a quantum field theory a bit better than closed string theory. So in closed string theory, you will always have a hierarchy of increasingly complicated contributions from the very depths of the moduli space. The moduli space is really complicated. So you might have something with a lot of handles which you cannot cut in any possible way. While things with boundaries can always be cut into simpler chunks in a manageable way. So this is the reason people can use open string field theory to do something, and nobody has been able to use closed string field theory to do something. But right, I don't know if I don't know how deep is this statement. I myself am a little confused.